Are you ready to do a little virtual lab now? We're going to find out the question to how could you design a solution to a problem? So I've not gone through this virtual lab myself, so we'll do it together right now, okay? I want to get myself out of the way, and then we'll get started. I'm down here now. Okay, here we go. Maybe.
Welcome to the lesson, How Can You Design a Solution to a Problem? In this lesson, you'll be presented with a problem that involves successfully dropping cargo from a plane. You are going to use a model to investigate what to use and how to use it to solve the problem. A modern car has many features that were designed to solve various problems. Can you identify some of them? Click each label to learn more.
Well, I like that car, don't you? Tinted shatter-resistant glass.
Tinted shatter-resistant glass reduces glare and improves safety.
Aerodynamic shape.
A smooth aerodynamic shape reduces wind resistance and fuel use. The gas inside halogen bulbs helps them give off more light and consume less power. Anti-lock brakes give drivers more control on wet or icy roads. Ergonomic seats are designed to better fit the human body and improve passenger comfort.
All right, tell me where I can get that car. That's cool.
To design a solution to a problem efficiently, you usually carry out a few steps. Can you put the steps in the correct order? Drag your answer into position and then click OK.
All right, I think we know this. We just looked at it. First, we find the problem. Then we plan and build to try to fix the problem. And if it doesn't, then we've got to test our plan. And if it doesn't work, then we redesign. And then after we're done, we've got our perfect model, we communicate the results.
Good job. This is the correct answer. An efficient process for designing a solution to a problem includes these key steps in the following order. Find a problem, plan and build, test and improve, redesign the solution if needed, and finally, communicate the results. You can look around and see a number of everyday items that have been designed to solve problems of safety, comfort, and efficiency. Click the image to learn more.
Okay.
A ballpoint pen eliminates the need to refill a fountain pen. An air-filled or pneumatic tire reduces discomfort caused by a wheel traveling over a bumpy surface. A car safety belt helps to prevent injuries to passengers on impact. The coating on this pan stops food from sticking to its surface. Eco-friendly detergent that breaks down naturally reduces damage to the environment. Spiked sports shoes prevent athletes from slipping on soft surfaces. The stay-on pull tab on a soda can reduces injuries and littering.
So all of those have been designed solutions to make things work better, help our environment, make it easier to do something, make it safer.
Not all design solutions involve making objects. The solving of many problems involves figuring out a way to do something to meet certain conditions. Let's look at an example. A farmer is away on vacation. You are given the job of feeding some of the animals each morning. However, the only information he left is as follows. 1. The horses should be fed before the chickens, but after the sheep. 2. The cows should be fed after the chickens. 3. The turkeys should be fed after the sheep, but before the horses. You must design the feeding schedule to match his instructions. How would you go about solving this problem? Can you fill out the feeding schedule correctly? Mark the schedule in the table by entering an X in the correct cells. When you're done, click OK.
Oh my goodness, this is hard, isn't it? So let's see. The horses should be fed before the chickens, but after the sheep. So the sheep are the first so far. Turkey should be fed after the sheep, but before the horses. So we've got to feed the sheep first. So I can see that from my clues here. So I'm going to feed the sheep at 7. Okay. The horses should be fed before the chickens, but after the sheep. Okay. Does anything else come after the sheep? Turkey should be fed after the sheep, but before the horses. So before we can feed the horses, we've got to feed the turkeys. Crazy turkeys. And then the horses. Okay, the cows should be fed after the chickens. Well, when are the chickens fed? The horses should be fed before the chickens. Okay, but after the sheep. So chickens at 7:45. What's left? A cow should be fed after the chickens. Does that work? I think we got it. That was some pretty lucky guesses, but we just followed the clues.
You can start by observing that this is an ordering problem. Once you know the order in which the animals should be fed, you can fill in the schedule. One approach to solving the problem is to write the names of the 5 types of animals on pieces of paper and place them in any order. Then, starting with the first piece of information, you can move enough pieces of paper to make sure its conditions are met. You could then repeat this process for the remaining 2 pieces of information. By the time you're done, you should have the animals in the correct order, so you can fill in the schedule as follows. Sheep, 7 a.m. Turkeys, 7:15 a.m. Horses, 7:30 a.m. Chickens, 7:45 a.m. And cows, 8 a.m. How did you do?
We got it, because we are smart.
In this activity, you're going to investigate the design of a solution for the following problem. A plane is going to drop cargo that has a parachute attached. The cargo must land intact and not farther than 10 meters from the landing target. Here's what you'll use. A parachute drop model. You will run the model to drop the cargo from the plane. Controls to change the parachute size. You will use these controls to select the parachute size. A control to change the opening altitude. You will use the altitude control to change the altitude at which the parachute opens. A distance measuring tool. You will be able to measure the distance of the cargo from the target on landing. A data table. You will record your data in this table.
Okay, I'm going to need your help on this for sure. All right. Send me your mental brain waves right now to help me out.
In this activity, you'll explore the problem of dropping cargo from a plane so it lands in one piece and close to its target. You will investigate how the size of the cargo's parachute and the altitude at which it is opened affect the outcome. Make a prediction. How do you think the parachute size and its opening altitude will affect the outcome of the cargo drop? Write your answer in the box and then click OK.
How do we think the parachute size and its opening altitude is how high, will affect the outcome of the cargo drop? One thing I noticed down here, this flag is blowing, so there must be some wind blowing this direction. So if I'll drop my parachute here, the wind's probably going to make it go way over here, isn't it? But if I dropped it lower and maybe over here, maybe it would land on the spot there. I think a bigger parachute would stay in the air longer, don't you? And I think a smaller parachute would come down quicker. So let's say the smaller parachute would come down more quickly.
I just need to talk to you sometime today, so whenever you got a chance, if you'll come over to my room.
Okay.
Thank you.
You're welcome.
RTI folders, if you got any of those green folders, if you'll bring them when you can.
Okay, sounds good.
Thank you.
All right, and a smaller parachute would come down more quickly, we said. And what else? The parachute size and its opening altitude. The closer to the ground, the less it will drift in the wind. That's my prediction. You agree with me?
Continue to see if your prediction is correct.
Okay, how do we do this? I guess we move on this way.
You want to investigate what size of parachute and what opening altitude will result in the successful dropping of some cargo. You will be able to use a model to simulate the cargo drop while varying the parachute size and the opening altitude. Write your plan in the box and then click OK.
All right, so I want to stay at the lowest altitude of 200 meters. I'm going to use the smaller parachute. Okay, that's my goal, because I want it to come down quickly, and I want it to be close so it doesn't drift too much. So we want it to land right here. Okay, so our plan: use the smaller parachute and the lowest altitude.
Check your plan. Did you set a goal that include these steps? Set the parachute size.
Smaller
Set
one,
the parachute opening altitude.
the lowest.
Run the model. Record the landing distance of the cargo from the target and whether the cargo was intact. Repeat the steps for different opening altitudes. Adjust the parachute size and repeat the steps. If your plan does not include these steps, you can change it. Once you've finished, click the next button to move on.
Okay, we're ready to move on. Let's try this thing.
There are different ways to carry out an investigation like this. Here is one way to do it. The parachute size is set to 15 square meters. Set the opening altitude to 600 meters.
Okay, I guess they're going to tell us how we have to do it.
Record the altitude in the table.
So the opening altitude, we put it at 600 meters. Did that. What next? Come on, Mr. Parachute, land. Well,
Use the measuring tool to open it and record the landing distance from the target flag.
okay, so it's, what do you say, about 9?
Enter the distance in the table.
About 8 meters. Okay.
Record here whether the cargo landed intact. Enter yes or no for each entry in the table.
Did it land intact? I can't tell. Did it bust? I'm going to say yes. I can't tell. I hope it's intact.
Click the reset button.
Okay.
Now, repeat the steps for 2 more parachute opening altitudes.
Okay, so let's try our original plan. Let's try the lowest altitude with the smaller parachute. Let's see what happens. Not good. Okay, so opening altitude was 200 meters. Distance to the target, oh my. That, well. $43. There we go. This isn't working right. About to get it, I think. 36 meters. That was far away. Is it intact? No. It's busted. All right, let's try the middle one. Let's go to 400 meters. Got to reset it, don't we? 400 meters. The small parachute. Let's see how it goes. It doesn't look good either to me. Maybe. Oh, it busted. So it's not intact. Let's try it out here. Here's the pole. Scoot over. And it's right here. So we're like 28 meters. Okay.
Click reset, and then click the control to change the area of the parachute to 30 square meters.
Okay.
Run the model for 3 different opening altitudes again and record your data in the table.
Well, we'll just start with the highest from 600 meters. And let's see what happens. Definitely slower. It's looking pretty good, though. Oh, okay. How far was it away? About 19 meters away. Okay. Is it intact? Yes. Okay, let's reset it. We'll try 400 meters. Type it over here. Go, Mr. Plane. Uh-oh. Where's, oh, shoo. Okay, well, I didn't think that parachute was going to open. It's intact. Let's see how far away it is. I can figure this thing out a little bit farther. It's about 22 meters away, isn't it? So farther away. Okay, let's reset it. We're going to go down to 200 meters. And here we go. Open parachute, open parachute. Oh, that's bad. It's busted. So no, it's not intact. And it's definitely far away. Let's see how far away it is. Like 35, 34 meters. Okay, so I don't think we probably should use the big parachute because it has to be within 10 meters, doesn't it? So that one didn't work. All right.
Analyze your results. Remember, the goal was to make sure the cargo landed intact and was not more than 10 meters from target. What parachute size and opening altitude enabled you to solve the problem? Was there more than one solution? Write your conclusions in the box and then click OK.
So the only one that landed within 10 meters was the parachute, the smaller parachute, the 15 millimeter parachute with the altitude of 600 meters. It was within 10 meters. So we should use the 15 meters squared. I can't put that on my computer. 15-meter parachute at an altitude of 600 meters. That's the only one that worked for the criteria we had to meet. Okay, let's move on.
When the smaller parachute was opened at too high an altitude, it landed too far from the target because it was less accurate. However, at too low an altitude, the cargo broke upon landing. To solve the problem, a medium opening height could be used with a smaller parachute. If a larger parachute was used, the opening altitude could be different because the bigger parachute slowed the cargo's fall more. There was more than one solution to many problems because there were usually several factors that affect the situation. How do your conclusions compare to how scientists explain this? Write your answer in the box and then click OK.
We're just going to move on.
Think about the cargo drop problem again. You needed the cargo to land intact and within a certain distance of the target. You investigated altering the size of the parachute and the opening altitude to find a solution. Are there other factors that might affect the cargo drop in a real situation? Can you list some? Write them in the box and then click OK.
So what do you think? What other factors would make this fall differently? Well, one we said already was the wind, right? The wind is going to affect how it falls. How about this plane? Not only do we need to know how high it is, but maybe how fast the plane is traveling. That's going to affect it, isn't it? The faster it goes, the probably more it's going to want to drift Can you think of any others? Well, I think that's good for now. Let's move on.
In a real situation, changes in the speed or direction of any wind or of the plane when the cargo is released are other factors that could affect the accuracy of the cargo drop.
I think we got it.
The plane is about to drop some cargo again. This time, you can also adjust the plane's speed. Run the model a few times for different parachute sizes, opening altitudes, and aircraft speeds. How close can you land the cargo to the target flag while keeping it intact? Record the data for your 3 best attempts.
Well, I think the last one, we got it to land pretty close at 600 meters with a smaller parachute, but we don't know how fast this plane was going last time. We'll just start at the slowest, and we'll adjust it and see if we can get right on that flag. No. Okay, so a parachute size of 15, and I can't do that meter squares. We're just going to put 15. Opening altitude, we had it at 600 meters. Plane speed was 200. The distance, we didn't measure that yet, did we? Okay, so I keep clicking on the wrong thing here. Come on, mister. So we're like 26, close to 27 meters away. So what do you think we need to change? It fell too far, but I think if we were less high, if we lowered the altitude of the plane, it would have less time to fall. So it would be closer to the flag. So let's go down to 400 meters here. We got to reset it. And let's see if we're closer to the ground. If it has less time to fall, it'll get closer to the flag. Here we go. Well, what do you think? It hit. It's definitely closer, but it's not intact. So that was no good. We're not even going to record that as our best attempt. What if we dropped it from 200 meters? Let's see. We're going even lower. And the plane's traveling slowly. I don't know why it wouldn't work. Let's try it. Open parachute. Open parachute. Well, that was just terrible. Okay, so let's try again. Let's speed the plane up and see if that helps any. I think it's going to fall farther away because this plane's going faster. So what if we made it going faster, but we actually got it 600 meters. We got pretty good. At least it didn't bust. This time we're going to go plane speed faster, see what difference that makes. Looking good so far. I don't know. He's traveling pretty far away. That's even farther. I'm not going to measure that because we see that's far away. Let's just go ahead and set the speed to the highest speed and see what happens. Yeah, I think it's going to drift even farther. So I think the pattern we see here is with the smaller parachute, the faster we're going, the farther away it is. Okay, so let's try, I don't know if we tried, let's go back down. Lower our altitude a little bit and stay at that high speed and see how that goes. Not good. Okay. Let's stay at a lower speed at that altitude. Let's go back to 350. See how this works. I don't remember trying this. A little better. Let's stay at this middle altitude and go the low speed. Oh, that's not looking too bad at all. But it busted. So I think we're going to have to go to this bigger parachute. Let's try reset. Let's try the highest, the slowest, and the biggest parachute. Let's see what happens. This is looking pretty good. Wow. Yes, that was awesome. So you couldn't get much better than that. So with the biggest parachute at the slowest speed and the highest altitude, how far are we away? Like 1 meter. That is awesome. So let's record that. We're only 1 meter from the target. We used a 30 size parachute. We were at 600 meters and the plane speed was 200. I wonder if we went just a little bit faster, if it would bring it on over on right on top of that flag. Do you think we can get any closer? I don't know if we can get any closer than that, but let's take it at like 250. And let's see, that would be right there. So we're only thing we're changing is we're speeding the plane up by 50 kilometers an hour. See what happens. Come on, land on that flag. Land on that flag. Boom. Oh, we just got on the other side of it. Okay, before I record it, I know we're supposed to do our best three. What if that went on the other side? It was on this side, so what's between 200 and 250? Let's put it at 225 and see if it lands right on it. You want to? So 225. I can't set 225, but I can set it at 220. Go. Land on that flag. Yes, looking good. Oh, yeah, we're right on it. We figured it out. So the best thing is to have that size 30 parachute with an opening altitude of 600 meters. The plane speed, what do we set it at? 220. And the distance to the target there, I'm just going to put 0. It's right on it. Good job.
Before we finish, let's take a look at the main points you covered. You've learned that solutions can be designed to solve problems. An efficient design process involves a few key steps. Find a problem, plan and build, test and improve, redesign the solution if needed, and communicate the results. A solution to a problem can be an object or a way of doing something. A model can help to design solutions to a problem. Now that you've finished the lesson, click the lab report button to save or print.
All right. Well, I know you just had to watch me have fun on that, but you might want to try to find a game online. I'll try to find one if I can, and do your own solution tests like that, or try to find the solution to a problem like we had there. You don't have any assignment for science today because this was kind of long videos, so enjoy. No work for science today. Maybe you can go find a game like the one we just played to find a solution to a problem. We'll talk to you later.